You have been shown that large and/or fast aircraft have high stick forces because of the large hinge moments generated. Stick forces that are too high make an aircraft difficult for the pilot to control. If aerodynamic balance cannot provide the required assistance to the pilot, powered flying controls must be used. Powered flying controls are hydraulically operated, either using a tapping from the aircraft main hydraulic system or alternatively using completely self-contained power packs. Powered flying controls can be divided into two categories: power-assisted and fully powered. We will start by looking at power-assisted flying controls. In a power-assisted flying control system, the Power Flying Control Unit, referred to as a PFCU, provides most of the force necessary to reduce the hinge moments. The pilot normally provides only the remaining force. These first few animations merely show the sequence of the operating principle. When the pilot moves the control column, you can see that both the control surface and the servo valve are moved. Movement of the servo valve provides a path for hydraulic fluid under pressure to one side of the PFCU piston and opens the other side to return. However, the piston cannot move because it is connected to the aircraft structure. But the PFCU body is free to move the control surface. The reason for this design arrangement is to make sure that the control surface is moved to the angle and at the rate required by the pilot. This is called follow-up. The force from the hydraulic system moves the body of the PFCU and the control surface until the input from the servo valve is cancelled by the motion of the PFCU body. A hydraulic lock now exists. In reality, as soon as the pilot starts to move the cockpit control, the PFCU immediately moves the control surface to the angle and at the rate of motion commanded. It can be seen that a small proportion of the aerodynamic force generated by moving and holding the control surface into the airflow is still felt by the pilot as stick force, so the natural feel of the controls is retained. The stick force will change in proportion with the square of the IAS, as it would in a purely manual control system. If hydraulic pressure is lost from a power-assisted flying control, the pilot would still be able to control the aircraft, but with significantly higher stick forces. Power-assisted flying controls, therefore, do not require a separate manual reversion system. If the speed or size of an aircraft dictates, a fully powered system will be fitted. As before, these first few animations merely show the sequence of the operating principle. When the control column is moved, the servo valve directs the hydraulic fluid under pressure to one side of the piston and opens the other side to return. The body of the PFCU will move the control surface until the body reaches the position of the servo valve, and then it will stop. The fluid in the PFCU is now trapped, giving a hydraulic lock that prevents any movement of the control surface by the airflow. In reality, as soon as the pilot starts to move the cockpit control, the PFCU immediately moves the control surface to the angle and at the rate of motion commanded. In the fully powered system, there is no mechanical connection between the control surface and the cockpit control. Therefore, the pilot has no stick force or feel at all and could accidentally overstress the aircraft. Previously described devices merely reduced the stick force or feel to manageable levels. There was always an aerodynamic force present at the cockpit control to give a sense to the pilot of the input made. In other words, the pilot could feel the input they had made on the cockpit controls. This feel is essential. A device must be incorporated in a fully powered flying control system to duplicate the required stick force or feel artificially. The artificial feel unit responds to changing dynamic pressure in the same way as an airspeed indicator. And because the symbol for dynamic pressure is Q, the device is also referred to as Q-feel. As before, these illustrations are schematic to show the operating principle. If hydraulic pressure to fully powered flying controls were lost, the aircraft would become uncontrollable. So some alternative means of control must be provided to guarantee safe flight. This can be done either by manual reversion or designing redundancy into the power flying control system. Manual reversion can be achieved by either servo tabs or spring tabs. In the event of hydraulic failure to the PFCU, a valve automatically opens to provide a path for the fluid across the piston. This cancels the hydraulic lock and allows movement of the control surface by either a servo tab or spring tab. Redundancy involves the use of multiple, completely independent hydraulic systems to power the flight controls. Each control surface can also be split with each segment powered by a separate hydraulic system. For modern jet transport with only 3 and more commonly 2 gas turbine engines, a ram air turbine or RAT is fitted to maintain adequate redundancy. In the event of an engine and/or a pump failure, the RAT can be deployed to provide a hydraulic flow to the primary flying controls only. To summarise, power flying controls must be used on large and/or fast transport aircraft that have control forces too high for the average pilot. Power-assisted controls retain some of the control's natural feel, but most of the force required is provided hydraulically. Fully powered controls use hydraulics to provide all the force needed to move the control surfaces into the airflow, but there is no direct link between the pilot's controls and control surfaces, and therefore an artificial feel system is required to give the pilot the stick force necessary to fly the aircraft safely.